This is part of our special EDS seminar, so focusing and celebrating our first cohort of working groups at ESIIL. So today we're welcoming Dr. Youmi Oh. She is the PI for AI for Natural Methane, which is a group that's reached now around 50 researchers, spanning diverse expertise in modeling and observations. She studies how environmental change alters surface-atmosphere interactions with bottom-up biogeochemistry models, top-down atmospheric chemistry and transport models, and knowledge-guided machine learning for her research. So with that, I welcome Youmi. Take it away.
Yeah, thank you, Rachel. Nice to meet you. I'm sorry that I cannot be there, but today I'm very happy to introduce our AI for Natural Methane Working Group. Probably of you joined the Innovation Summit last month, and you have heard from me of what we have been working on. So this presentation is more focusing, like I try to focus more on science part of our working group. So the title is Next Generation Modeling of Global Natural Methane Fluxes by Integrating Multi-Scale Observation with Knowledge-Guided Machine Learning. And as you can see, we have a lot of people listed in this slide. So we have now more than Rachel, like I think now we just added two more people. So like 61 people on our listserv. And we have been working really hard to make progress on our projects. So I'm going to show you some of the example. So this is a group effort. I'm just here to represent our group, but we have these four PIs working together, me and Lichong Liu at the University of Wisconsin-Madison, Sparkle Mellon at Yale University, and also Gavin McNichol at the University of Illinois, Chicago. So this is our working groups. I made this slide for the site visit, and I really like this slide. So our working group this is a community effort to harmonize the natural methane data set using knowledge-guided machine learning. And so now we have more than 50 researchers from university, federal agencies, and nonprofit organizations. So you can see the logos. I just selected a few of them that represent our working group. So we have people from NASA, NOAA, NCAR, two different DOE labs, and also nonprofit from Woodwell Climate Research, Spark Climate Solution, and also our PIs are from these universities. And we also have 25 other universities that are also joining our working group. And this picture on the left is our workshop in 2025. So you can see we have a lot of members joining us last year. Not only the affiliation, we also bring together experts from biology, ecology, atmospheric science, computer science, and advanced AI ML field. For example, we have two grad students in computer science. They are really experts in advanced AI machine learning techniques, but then they are learning more about our domain science. So we are really truly diverse group that integrate this scientists from who knows the domain knowledge, but also the computer scientists together. This group was only possible due to ESIIL's amazing support over the last 2 years. The infrastructure and cybers and all this administrative help has been extremely helpful to have our working group to be very successful. So this ESIIL's convergent science approach really enable us to get together and do the methane discovery beyond any single field because methane is a complex problem and we have to collaborate with many different fields together so that we can solve this methane issue. So from this presentation, as I mentioned, we have three main goals in our working group. First, harmonize the natural methane data set, which is the main goal of our project. But second one is do some cool science with our harmonized data set and also knowledge-guided machine learning. And the third one is increasing AI literacy in our group and also across our domain network by having multiple tutorial and providing the open source package. But since I already presented this during the Innovation Summit, I will really focus on the science that we are doing, especially the first part that I will focus on is about methane. So our working group's name is AI for Natural Methane. So the first part I will focus on why natural methane is important and why it's interesting. And the second one is AI part. So why we need KGML, knowledge guided machine learning, and why do we need to do the data harmonization? So this is methane part, this is AI part, and the third part is our group's KGML application and scientific discoveries. So each part has about 10 slides, and I tried intentionally. I will pause after each section so that I can get many questions from you. If you have any questions, please ask me after each section. So I will go to the first part, why natural methane is important. What is natural methane? So I will explain a little more details and why methane is important. So this is definitely, as you all know, methane plays a very important role in Earth's energy budget. So this plot on the left shows the radiative forcing changes since 1980s to 2023. What is radiative forcing? This is how much these different greenhouse gases can trap heat in the atmosphere. And here you can see carbon dioxide. I'm not sure if you can see my cursor. Probably. I'm not sure how I can. Do you
We
see
can see
my
it.
cursor?
Yeah.
Yeah.
Oh, interesting. Okay, thank you. Yeah, so carbon dioxide is the definitely big elephant in the room. It has the largest effect on radiative forcing, and the next gas is the methane. However, if you think about the concentration difference, methane in the atmosphere is about the concentration or mole fraction is about 2 ppm, whereas carbon dioxide is about 200 times larger, 400 ppm. However, you can see the methane's radiative forcing, the ability to trap the heat is quite large. It's because methane has 28 to 36 times the warming power of carbon dioxide over the 100 years. So basically, one methane molecule can trap heat as effectively as 30 CO2 molecules. Then what's the effect of these different greenhouse gases on temperature increase? Because eventually, I think it's really important to understand how they're interacting in the atmosphere and then increase the temperature. So this plot shows the contribution of warming in degrees Celsius. So what you can see is carbon dioxide has increased the global temperature by about 0.75 degrees Celsius. So compared to the pre-industrial revolution time period. And methane has increased the temperature quite a lot, about 0.5 degrees Celsius. Why is it so? Why is methane has a disproportionately large impact on atmospheric temperature increase? Because methane reacts in the atmosphere and then produce other greenhouse gases. The examples are ozone, water vapor in the mid-atmosphere, and also aerosols. So methane is pretty reactive in the atmosphere, so it has a shorter lifetime compared to carbon dioxide, which is about 10 years. But the fact that methane is reactive in the atmosphere give us an opportunity that if we are reducing methane right now, we can see the changes in 10 years because it has a very short lifetime. So this paper by Sun et al. 2021 shows that if we are having an ambitious action on only CO2, then we may have this overshoot of temperature increase in the mid of the centuries. However, if we are putting our ambitious effort on both methane and CO2, then this overshoot may not happen. So methane is a really good short-term climate target. So what's actually happening? So we have to reduce methane really quickly. But what we are seeing in the atmosphere is a very rapid increase in atmospheric methane. To give you some reference point, I am giving you this long-term methane on the left changes and long-term CO2 changes on the right. You can see CO2 has increased pretty steadily and compared to the pre-industrial time period, CO2 concentration has increased by about 40%. Whereas for methane, atmospheric methane has increased more than 3 times compared to the pre-industrial time. And also there is an interesting long-term trend. So if I just focus on the annual growth, I can compare this atmospheric methane change for 3 different time periods. That from 2000 to 2006, there was no increase in atmospheric methane at all. And before that, there was a slowdown of this atmospheric methane growth. And after that, there was a rapid increase in atmospheric methane. And this plot on the right shows the annual growth increase of methane. So basically a derivative of this plot. And what you can see is 2020, 2021, 2022, there was the largest increase in atmospheric methane that we observed since our NOAA's measurement started back in 1984. This is a pandemic year. Why is it increasing so much during the pandemic year? What is happening? So this is still a mystery, and it gives a warning, like it's a very alarming because we need to reduce methane right now, but there is a large increase. Not only that, our methane increase is approaching the warmer scenario. So this is the future prediction of projection of methane until 2050, and there are different projection scenarios, SSP scenarios. What you can see is in 2024, our atmospheric methane concentration reached 1930 ppb, which is reaching to this warmer scenario that could increase atmospheric temperature by 4 to 5 degrees Celsius. So we unfortunately we have to reduce methane right now, but what we are seeing in the atmosphere is a really rapid increase. So why is it increasing? Is it related to natural methane? That's what I'm going after. So methane, where is methane emitted and removed? How is produced and how is removed? So atmospheric methane level is pretty complex and is determined by the multiple sources and sink. And the source can be divided into four main categories. The first part is fossil fuel emissions. So the natural gases main component is methane. So about 70% of the natural gas is methane. So when there is a leak, when you are producing or transport your natural gas, there is a large methane leak, and that goes into the atmosphere. And also methane is emitted from core geologic sieve. Another big portion of the methane is emitted from cow, as you know, cow farting and burping. There are microbes in cows' intestine and in digestive system, and these microbes make methane. And there are also microbes from this wastewater rice farming facilities that they make methane. Another big portion is natural microbial, so natural methane. So this is also a big portion of methane source, about 30%, and wetland is the largest source of natural methane. Another natural microbial methane. And the last one is there is a small methane emission from the incomplete combustion of biofuel and biomass burning. What about sink? As I mentioned, methane reacts in the atmosphere and then it makes other chemicals that is also greenhouse gas. So that methane has a larger impact on temperature. So what are the gases that the methane is reacting with? The biggest portion is hydroxyradical OH. So tropospheric OH is a big portion, and there is another portion from chlorine, O singlet D. And there are microbes that are also eating methane in the soil. So it's called methanotrophs. So as you can see, methane is pretty complex. It not only have anthropogenic part, but also natural part has a large variability. And there are sources and also sinks. So it's really hard to understand methane, especially, it's because it's really hard to distinguish them. So I wanted to just mention one thing, like my main job at NOAA is running this carbon tracker methane. Carbon tracker methane is atmospheric inversion system that use atmospheric methane to back calculate methane and isotope to back calculate how much methane is emitted from this different part. So by using this data on simulation system, we can understand how much methane is from different part. And this is the result that I wanted to show you. So I wanted to advertise this paper because it is currently in press and Nature Communications. So you will see my paper in 2-3 weeks. Very exciting because it took a really long time to get published. So what this plot is showing you is a long-term change in methane emission from different sources: total, microbial, fossil, and pyrogenic. And there are two different scenarios. The blue scenarios use methane and methane isotopes, so additional constraint. So we consider that blue is more complete scenarios that use all the information. What you see is atmospheric methane has increased a lot over the last 2 decades. So the total emission increased by about 15%, which is a really large increase. And also microbial emission dominate the atmospheric methane growth. So methane increase was based on our blue scenarios that use isotope as well. That shows that microbial emission has been increasing a lot and it dominates the methane growth. So as I mentioned before, there are multiple different microbial sources such as rice, um, ruminants, wetland. What is making this methane increase? To do that, the answer is all of our increasing, but that we especially focus on 2020 to 2022 period when there was a large increase, and we try to understand if there is a correlation with terrestrial water change. So what we did was we divided the globe into 12 different regions where there are major wetlands are located, and we compare the terrestrial water changes. This is from the GRACE satellite and our simulation. And what we found is that there was a large increase in wetland emission, especially in Africa. So this plot shows the West Africa methane and water change, and Southeast Africa methane and water change, Southeast Asia, so this region, water and methane change. And what we saw is during the 2020-2022, the largest methane increase, there was a large increase in terrestrial water, so it was more wet, and that caused the methane to increase in these regions. So in summary, it shows that this natural wetland methane feedback is very important. And in 2020-2022 period, what we show is that there was an increase in inundation. So the soil gets really wet, and that makes the wetland methane emission, natural methane, to increase, and that increased the atmospheric methane. And there's a positive feedback because atmospheric methane increased the temperature. So there is a positive feedback of this microbial source. And there are other studies also shows that some studies show that there is some recent intensification of wetland methane feedback. And also during the past glacier termination, there was a really important natural methane feedback going on. So yes, from here, going back to the complicated plot, we show that this wetland is one of the most important source of methane that could cause the large variability in atmospheric methane. And that's what we are focusing on in our working group. So just a summary, why natural methane is important. Natural methane sources are critical for understanding past changes in the methane budget and will become increasingly important in the future because of the climate feedback. We therefore need to better quantify these sources and understand how and why they change over time, which is the objective of our working group that use advanced AI technique. Yes, so here this is the first part of methane, why is it important and interesting. I want to take some questions. Do you have any questions?
Thank you so much. This is super interesting. What is the relationship between, is the relationship between methane emission and soil moisture in a wetland, is it linear, or is there some threshold effects where once you get to a certain inundation that you start to see these large emissions of methane?
Yes, that's a great question. So in general, if the soil is not fully saturated, because the wetland usually, yeah. So if the soil is not fully saturated, so if the soil still has moisture but not fully, then the surface layer can be still dry, and then that can consume all the methane by methanotropes. So in our case, we are considering the inundated area that's fully saturated. So the surface is also covered by water. So when this condition happen, then the methane can be emitted to the surface through different transport processes.
Thanks.
Did I answer your question? Yeah.
Yes. Yes. Thank you.
Okay. Okay.
Kind of on that note, at what point is natural methane release considered anthropogenic, especially in the face of anthropogenic climate change? Is that still considered natural if the source is technically a natural source?
That's actually a really great point because in my case, in my understanding, yeah, because climate change, if it's and climate change is due to humans, then this natural microbial increase happening, if it's because of this temperature increase and the interaction with this climate change, then I think it's also not anthropogenic, but in currently our definition of anthropogenic methane emission is directly like from human activities. If there is a active use of natural methane, natural gas, and if there is a leak, then we consider that as anthropogenic. So yeah, that's a good point. Like cow, they will not make methane as much as now if we don't like have them, or rice if we don't have a farming system. So yeah, we consider those as anthropogenic, but you're right that natural microbial can be also anthropogenic
Thank you.
due to climate change. Yeah. More question, I think I can move on first, but you can ask me at the end because I think many of you are here not because methane is interesting problem, but also AI, what our working group is have been working on. So we applied the KGML knowledge guided machine learning on this natural methane source problem, especially wetland. So why are we using KGML, and why have we been working on the data harmonization? To understand that, we have to understand what is knowledge guided machine learning. So I have a few fun slides about knowledge guided machine learning. And I think you can apply this to your own research and science. So you have seen this slide many times. What is knowledge guided machine learning? Knowledge guided machine learning is a really broad term to basically combine our process-based knowledge into the machine learning model, because both process-based model and machine learning models have pros and cons. For example, process-based model is based on the physics and biogeochemical parameters, so we understand the equation. However, it's very sensitive to parameterization. Whereas machine learning model is very fast, however, it's often criticized by its black box, so we don't understand the mechanism, and we need really large training data set. That's the major bottleneck for natural methane research, because it's really hard to measure natural methane. So yeah, we don't have large training data sets for in our science compared to like climate, let's say temperature, because there are a lot of reanalysis data. So here we are using this knowledge guided machine learning that complement both methods. But still, yeah, I know this is conceptually I understand, but what is it? So I am giving you a very fun analogy, KGML analogy. So this is what Lee Chang Liu, our tech lead and co-PI, he found out this, fun analogy of robot learning cooking skills. So imagine that you are making, let's say, pesto pasta. What are the ingredients of the pesto pasta? Pasta, salt, oil,
Pesto.
pesto. Yes, exactly. So this black box ML model is basically you are giving all this ingredient without information and asking it to make a pesto pasta perfectly. Very difficult task because you have to go through a lot of trial and errors. Whereas there are three knowledge guided technique. This is just example. There are many other ways, but there are three examples that you can add your knowledge into this machine learning model to be smarter. The first one is knowledge guided pre-training. So basically, you can ask this machine learning model to see lots of YouTube video of how to make a pesto pasta. So you can observe the chefs and basically learn from the chef and before it actually it learns from the chef like how to make a pesto pasta. The second one is knowledge guided loss function. So following the cooking rules. So you can teach the machine learning model that if you put too much oil or salt, it's not good for your pasta. So giving some rule is the second one. And the third one is knowledge guided architecture. So you're basically giving the recipe and the order Like, oh, here's the first step of making a pasta. You have to boil the pasta. Second step, you have to make a pesto sauce. And the third, you have to mix them together. So here are the ways how you can make your machine learning model to be smarter to make the pesto pasta more successfully. And we are applying this knowledge in our working group, actually applying this knowledge into our science. So I'm going to show you some examples, but here are the specific case that how we are adding this knowledge into our machine learning model. And I hope these examples are useful for your study so that for your research, you can also apply this into your science. So the first step is black box basic ML model. This is the basic how ML model works. You have some kind of ML model, random forest, GRU, LSTM, whatever model you have, and you use the real world data to train your model. So in our case, our label is methane flux and our input parameters are temperature and precipitation, for example. And after you train your ML model, optimize it, you use the new data up to extrapolate to the whole global scale. So this is how we are usually doing our methane flux prediction. And here is one way how you can do the knowledge guided pre-training. So before the training step, before you actually use the real world data set, you can train your model by using the synthetic data. Lots of synthetic data can be possible, are available. For example, process-based model can have an ensemble simulation and have lots of pre-training data set of your label and also input parameters. So from these steps, you can pre-train and then pre-train your model and then further fine-tune it by using the real-world data set. The second one is knowledge-guided loss function. So this loss function seems complicated, but it's basically very simple. You try to optimize some parameters so that you can reduce the bias between observation and simulation, so that your simulation can resemble and can match better with the observation data. So that's what this function is. However, here we are adding knowledge-guided loss. What it means is you can use some mass balance equation that you already know in physics or biogeochemistry, so that this loss function can add an additional penalty into your loss function. So in our case, we are adding some temperature and soil moisture constraints. So as an example, the good question that you asked me, if the soil, for example, if the soil is not fully saturated, then you're not giving any methane emission. That's an example of the knowledge guided loss that you can put it in your equation. And the last one is knowledge guided architecture. So you can make this machine learning model to be complicated so that this machine learning model have several sub-modules that also have intermediate variables that you can verify using the observation. So in our study right now, in our working group, we are using all these three different techniques, and I will show you some examples in our third section. Before getting into the example, I'm going to show you the importance of the harmonization. Sorry, I forgot to mention this slide. So if you're interested in this KGML, there's a Python KGML package available on our website, on our AI for Natural Methane website. And also you can go through, Lee Chong is managing this Python KGML package. So you can also get into this Python KGML by typing that online. Yeah, so it's you can use this package in your science, and also if you have questions, please reach out to us. And we also have been providing the tutorial of the KGML to our working group members in 2024 and 2025. So getting back to science, okay, now I understand what is KGML. Oh, that's pretty useful. But why do we need this for natural methane study? Because there is a large uncertainty in this natural methane model and observation data. And currently, our case, we are really focusing on wetland. So here are three different types of observation that we can get from in the field. So the first type is chamber data set. So chamber measurement is usually if you go to the field and they put the bucket and you try to understand the methane flux from the very small area. So the footprint is really small. Whereas EC tower measurement, I'm sure many of you are very familiar with this Korea's tower network because you work with NEON as well. So EC tower measurements have larger footprint than chamber, but still I think it has a footprint of about 1 square kilometer. There is a big tower measurement. For example, NOAA in my lab, we have a 300-meter tower measurements that have a really large footprint of atmospheric methane. And from here, you can see that between the measurements, there are some discrepancy because they have different footprints. And also, there are big uncertainty in model estimation that use different observation. So this bottom-up model, for example, process-based model, using this small-scale measurement, you get much larger methane emission from wetland compared to the methane emission estimated from top-down, such as carbon tracker methane that use atmospheric methane observation. So that's a big problem in our field. We are trying to reduce those bias from different measurements and different modeling. However, there is still large uncertainty. So our working group tried to combine all this different model and observation result to harmonize data set using KGML. To do that, during our 2024 workshop, our first workshop, we first compiled all the data set. So we did the data, to do the data harmonization, we first compile all the model and observation data set, and the model include process-based model, biogeochemistry model, or atmospheric inversion model, such as carbon tracker that I'm running, and observation data such as EC tower measurements and chamber measurements. So these three type of measurements are they have usually unified format and nicely set up nice better data set than this chamber measurement because it was not compiled. So we put over the last 2 years, we put lots of effort to really combine all these chamber measurements, and now you can see that we have very comprehensive chamber measurements of natural methane that covers from 1980s to 2025. So this paper is currently Avani Malhotra, who is a scientist at PNNL, Pacific Northwest National Lab. She is working on the manuscript right now to have a result about this chamber data set. So for the second section, I hope I convince you why we need KGML and harmonized data set. This KGML integrates scientific knowledge with observation to improve accuracy, interpretability, and extrapolation. And our harmonized data set provides a multi-scale foundation needed to train, benchmark, and also apply KGML across model and observation. So from now, I'm going to show you some example of the study that used this harmonized data set and also KGML to improve for the scientific discovery. But before that, do you have any questions?
I have a question.
Yes.
Your group used for the KGML, your final KGML, you used all three of the knowledge-based approaches. And I was wondering how important is each one to the process? Like if you had to get rid of one step, is there one you would get rid of? Is it necessary to have all three?
Oh, yes, that's a great question. And then, oh, sorry, I think I misspoke. So we have three different papers that use three different technique, like knowledge guided architecture, loss function, and pre-training. But we have a paper that Li Chang Liu published in 2024 in Nature Communication that used all three. And he did exactly what you mentioned, which of this knowledge guided technique matter more to his own scientific question. And this is really like data specific and model specific and also the scientific question specific. But in his case, he found that this pre-training was the most important technique in his modeling. But yeah, it really depends on different models and observation.
Very interesting. Thanks. I'll have to check that paper out.
Yeah. It's you can just put this and his name and then KGML, and I think it's been already cited so much. And yes, any other questions?
I have a question about that chamber data trend, the last slide you had before the break. I see that dip in 2008 that you talked about in the first act. But then in 2020, here is actually a low dip instead of a really high spike like you showed in the previous one.
Oh, yeah, I'm sorry. Yeah, I'm sorry. This is not methane flux, but this is how many data points we have each year. So yeah, it doesn't really represent methane flux changes.
I see.
But
So
that's a good question. Yeah.
So in the COVID year, we actually had a lot fewer data points, even though we show
Yeah.
really strong growth. Right, cool.
Exactly. Which is, yeah, pretty natural because during the lockdown, yeah, no one likes to go to field. I mean, people cannot go to field. Yes.
Awesome, thank you.
Yes, okay. Now I'm going to show you three examples, like two papers, mainly two papers, that our working group actually have been working on to use the harmonized data set and KGML to improve our science on natural methane. So the first paper is led by Yiming Sun, who is a grad student at the University of Pittsburgh in computer science. So she's very, very good at those AI machine learning technique, and she now understands our domain science in natural methane science really well. So she published this paper. It was just published 2 months ago. So please check it out. And this paper was published in the Computer Science Conference journal, and sorry, I don't this conference journal in computer science. And the title is X Methane Wet, a cross-scale global wetland methane emission benchmark data set for advancing science discovery with AI. So what it did was it didn't use all the harmonized data set that I mentioned here, but it used this one process-based model and one eddy covariance tower measurement. So it tried to combine these two. Going back, so yeah, again, same explanation. It used a process-based model that has its own pros and cons, and also observation is from EC tower measurement, which has also its own pros and cons. Using knowledge-guided machine learning, it tried to combine both of them. Before combining both of them, Yiming first tested multiple machine learning model to emulate each of these different observation and model data set. So this plot shows the model that she tested and the split that she performed. So here are 6 different models that she tested to emulate the modeled output from one process-based model. So she used LSTM, EA LSTM, TCN, transformer, pyroformer. So they all have pros and cons in representing temporal and spatial variability and also tension knowledge. So she tested multiple different models. And what she found is that to emulate the model output, LSTM is quite good, which is pretty interesting because LSTM is better at understanding this large temporal correlation and under variation, which is suitable for this modeled output because modeled outputs are usually more muted and then it has pretty uniform distribution so that it doesn't need to have a more attention to spatial variability. So this LSTM performed the best in representing the modeled output. And this plot at the bottom shows the mean methane emission and the mean RMSE here, and on the right is showing the R squared score. So what it shows is that if there is a very clear seasonality, usually the wetland emission has a clear seasonality depending on the temperature and soil moisture. And model is better at capturing the variability where there is a really clear seasonal cycle, especially in this Arctic and temperate region. Whereas in the tropical region, it had a small R square because it was hard for model to represent those regions because it doesn't have a clear temporal patterns. The second one is now Yiming is using the same 6 different models, but now she's applying this model to EC tower observation, actual observation. And as I mentioned, model data is easier to emulate, whereas observation data, actual observation is harder because it's sparse and also it's noisy. So out of the 6 models in her case, so these are the different locations of the EC tower, and she found that this pyroformer performed the best, but you can see that still the R square value is much smaller. This pyroformer performed better because this multi-scale attention model structure can capture both short-term fluctuation and also long-term dependency. That's more flexible than the LSTM model. So in her case, the pyroformer performs better at representing this EC observation. So our goal is eventually connecting the model and observation data together. So what we did was what she did was she used the different transfer learning technique to combine the model and observation together. So there are multiple ways to do this transfer learning. It may not be a new technique for you. There are multiple ways to combine, basically transfer the knowledge that you learn from the first step, pre-training step, and do the fine tuning. And here are the ways of doing it: fine tuning, residual learning, adversarial data transfer, re-rating. Those are all different ways of the transfer learning. And what she found is that using this transfer learning, the model represent the observation much better. So this plot at the bottom shows that compared to observation, which is blue, the basic ML model that just use the basic ML model, and advanced ML model is when you're using this transfer learning that use pre-training. So we are having this knowledge guided pre-training step. And this pre-training really helps to represent the observation across many different sites. So it shows that model data is actually helpful to learn generalize the deep learning model on EC tower observation. And here's another example of the study that we had that used not only pre-training, but also knowledge-guided architecture led by Chris Smith, who was working with me, who was a postdoc at NOAA. And this paper is now under review in GRL. And it shows that this model structure is pretty complicated, but basically he also used some type of pre-training step to combine the knowledge from the model into the actual observation data set. And he also used the high resolution MODIS reflectance to represent the heterogeneity of the spatial variability near the EC tower measurements. And then after that, he extrapolated to the whole globe, and this is the estimation of the wetland methane emission. And you can see that this spatial and temporal variability that we found is more reasonable than just the ML model. So yeah, those modeled knowledge is really helpful to train the machine learning model. And for our last study, this paper is more science driven. So this is led by Qing Zhu, who is a senior research scientist at Lawrence Berkeley National Lab. And this paper is just published last month, but in Global Change Biology. So what we did was we used knowledge-guided machine learning to reconstruct the long-term wetland methane flux from EC tower measurements. So what he did was there are 11 EC tower measurements that has at least more than 8 years of the data set. But 8 years is not enough for us to understand the long-term change, as I mentioned from the first section, that to understand long-term change, we need to have multiple decades of the measurements. So what we did was, so this is the data availability. As you can see that not many data towers have a long-term measurements. So what we did was we used the knowledge-guided machine learning to reconstruct this long-term methane fluxes from 11 towers. So how does this work? So for this, we are using knowledge-guided loss function. So there are 3 different techniques, and we are using one technique in this paper. So this is complicated, but basically very simple. You have some input, some model, and usually your loss function is determined by the model and observation bias. But here, your loss function is adding extra knowledge constraint And this constraint is from our prior knowledge, process-based knowledge. We understand that this first function is basically temperature sensitivity. From here, we understand that, oh, methane emission is usually having a temperature sensitivity of 2, which means methane emission increased by twice when the temperature increased by 10 degrees Celsius. We understand this range. So we are giving, based on the previous laboratory and the field experiment, we are giving this reasonable temperature sensitivity so that if the model is having too large sensitivity or too small sensitivity, then we are giving penalty to this loss function. There's another function of this methane flux and the GPP relationship. So basically, wherever there is a photosynthesis, then we think that the methane emission is also happening because GPP is a substrate for it's a source of carbon for methanogenesis, methane production. So it looks complicated, but basically we used some knowledge that we have from the process-based modeling and also prior knowledge to make our loss function to be smarter. Also, this is the result of our reconstructed methane emission over the last 25 years. So methane emission, FCH4 is methane emission over the last 25 years, which is very interesting that, each different towers have different variability. And what he found is that there is an interesting trend, long-term trend, that's dependent on latitude. So what you see on this plot at the right is showing you the trend, how is methane change over time, and how is related to latitude. And there's a positive trend, which means at high latitude, there is a larger trend in methane. So methane increase is larger compared to the lower latitude where there is like in Florida when there is, when the latitude is much lower, then the trend is smaller. This makes sense because as you know, in the Arctic, the warming happens much faster. So these microbes may be more sensitive to this temperature changes. So this latitude gradient shows that the Arctic is more vulnerable to climate change. And also Arctic may make more methane in the future, make more methane emission in the future from natural sources. So I think I can stop. This is just one slide showing that we compare with the model and showing that there is a large discrepancy between our observation compared to the model, so that the current process-based model needs to better represent the actual observation. So this plot just show, but if you're interested in, please have a look at our paper. And here's a summary. If you can, this is just summary from the first section. We learned that natural methane sources are very critical in explaining past methane changes and also important to understand future through the climate feedback. And the second section, we show that our AI for Natural Methane Working Group bring together the multidisciplinary expertise and harmonized multi-scale data set. And we are also using diverse machine learning techniques, such as machine learning, pre-training, loss function architecture. And from the third section, we actually show you some application that demonstrate that KGML can bridge simulation and observation, extend sparse observation, and also reveal the new methane trend and model data mismatches. So here is the end of this presentation. Oh, just want to emphasize that we also, now that we are moving on to we made our new website, aiformethane.com, and we are also always getting new members. So if you are interested in, please reach out to me, and also getting into the GitHub. There is a Google form that you can fill out that we can add you into our listserv. So and please check out our website. So thank you for listening. Thank you. That's it. Thank you. I'm sorry for the science savvy talk right before the busy day.
Oh, that was amazing.
The problem was
That's
the
awesome.
pesto analogy before lunch.
Yes, your lunchtime, noon. Yeah, I think I will have some pasta after this. Haven't had lunch. Oh, I got question from, sorry, from online audience. I have question from Fang Yao. Could you,
Hi,
yeah,
can you hear me
unmute
okay?
yourself? Yeah, I can hear you.
So great presentation, and I have a question for
Yeah.
your last paper that introduced. So in that paper, you highlight the trend in the larger trend in the high latitude area, and I think it's speaking to the trend in Alaska, and you link that to the Arctic warming. So my question is this large trend, large increase, more sensitive to the temperature or to the weather conditions, as rivers may have a larger discharge or lakes have higher water levels.
Mm. Yeah, Fang, that's a very good observation. You're right that the four point here in the Arctic region is from Alaska, because we have a Mariflux Tower network in the US only, US mainly. Um, in this case, Fang, because especially our model is very sensitive to temperature, and since the Arctic temperature, usually the increasing trend is larger, we are observing more on the temperature sensitivity. However, as you mentioned, soil moisture is very important. And as far as I understand, this Arctic precipitation it's a little more complicated than the temperature. Like temperature is just increasing, but the Arctic soil moisture pattern is a little complicated because when the precipitation increase, that can increase soil moisture, but there is also this thermokarst. So there is depression of the soil, surface soil level, and then that will also change the soil moisture. So I think that problem is a little more complicated. And I would say this foresight, because we are adding temperature sensitivity in our model, I think this is mainly response of temperature. But in reality, I understand that, yeah, those soil moisture variability is very important, which is not well constrained. Did I answer your question?
Yes, thank you so much.
Oh, okay. Yep. Yes, it's a very good question. Yes. One more question, or are you ready for lunch?
I did ask one. Yumi, can you hear me?
Yes.
Hi, I'm Samantha. I actually work at Neon. This was a great talk. Fantastic work. Um, I'm curious, that's such a cool thing that you were able to unite computer scientists, machine learning experts, biogeochemists, ecologists. Mechanically, how do you do this? I mean, how do you find, let's say you're an atmospheric scientist, how do you find computer scientists and AI experts who want
Mm.
to work with you and learn about methane and model methane? Is that something that ESIIL facilitates those connections? Do you just know people personally? Or like, how did you build this interdisciplinary group?
Mm. Yeah, that's interesting. I think we started from not like 50 people. I think we started from like 20 people at first, and um I think our four PI have good representation, actually. I think that really helps. Like I do atmospheric science and model, but Lee Chung, who I mentioned previously, he's an AI expert, although he's in bioengineering department, but he knows a lot of computer science people and is very familiar with very advanced AI technique. And Gavin and Sparkle, they are also modeler, but they also do observation. So they know a lot of people in observation field. So I think it really helped from starting from small group, and then we gathered about, I think we had about like 20 people at first, and this 20 people also bring another 10 people and another 30 people bring another 10 people. So now it's very interdisciplinary, and now we cover not only yeah, like one field, but all these different fields, people are all working together. And computer science people are usually interested in getting data. because they have very advanced AI technique, but they need some data to test their model. So they're always welcome to those kind of collaborations. So we have been having good collaboration with many computer science department and the faculty there. Yes, I know I'm out of time, but I got a question online, but I think I can answer this after finishing this seminar, and then I can answer this after. Yes. Thank you for listening, and
Thank you, Yumi.
yeah,
You're
see,
amazing.
yes. Thank you.